Thank you very much for that great introduction. Hi everyone. My name is Boris, and today I'm going to be talking about trajectory forecasting and some of our latest research on integrating it within the modern autonomous vehicle stack. So, in recent years, there's been a significant commercial effort in bringing robots to society in domains spanning autonomous driving, collaborative manufacturing, and assistive robotics, such as helping out in the home or healthcare settings. Now, of these, probably self-driving cars are the most visible examples, with some companies even recently obtaining permits to operate autonomously in some US cities. Accordingly, scenarios with human-robot interaction will soon be everywhere, and navigating them safely and smoothly is of critical importance. So taking an example from autonomous driving, one of the core challenges is that scenarios like merging onto a highway or driving through a four-way stop intersection are exercises in negotiation. And to show an example of what can happen when this goes wrong, in this video, we can see a highway merge leading to a near standstill, which is pretty dangerous on a road like this, as this is like a 3 or 4 lane highway. So as humans, we constantly make decisions by reasoning about what might happen in the future. And we use a mental model of how other humans behave, known sometimes as a theory of mind in psychology. Accordingly, reasoning about what might happen in the future is a critical capability. As a result, the goal of my research has broadly been to endow robots with the same capability. In other words, to build a computational model of human behavior. So in robotics, this ability to reason about what might happen in the future is generally known as multi-agent trajectory forecasting. And here's an illustration of what a set of forecasted trajectories might look like, with multiple arrows emanating from each agent indicating multiple possible futures. Now, I have to say, this field is very, very popular, and it's been, there's been a ton of research on trajectory forecasting. I'm taking a figure here from a review paper that was published towards the end of 2019, but since 2019 till now, there's been hundreds of more papers published. And in all of these, different research works, there's been a lot of effort focusing on improving how fast, different neural networks or whatever for trajectory forecasting operate, their accuracy, how diverse their outputs are, and different ways of incorporating context like maps, agent dynamics, and other extra information you might have available to the robot that you're deploying it on. However, one thing that I want to focus on today is that prediction or trajectory forecasting methods don't operate in a vacuum. And this rings especially true for autonomous vehicles, where prediction is a core component of the actual autonomy stack. And in particular, its inputs are taken from perception, and the outputs of prediction are used to inform downstream planning and control. So while it has this, core critical place within the autonomy stack, a lot of this research that I've described in the previous slide has not been really dealing with how to effectively integrate these modules together. And so today, in this talk, I'll be discussing some of our latest work in effectively integrating prediction with perception and planning, as well as then moving on to how to evaluate the whole stack holistically. And finally, I'll discuss some of our latest research work and propose a few hopefully high yield, open future directions. So very quickly, when we discuss integration between modules in the autonomy stack, this very quickly becomes a discussion around robustness and addressing how to propagate uncertainty through the stack. So one example that I'm going to show here is a case where an object detector in an autonomy stack might produce some uncertain output, or a tracker might produce some uncertain output. And so you can see that if something that you're detecting is a little bit fuzzy, or you might not know where its position is, that is then going to influence how you track it through time. It's going to influence how you predict where it might go in the future, and it's definitely going to influence how you think about it, let's say from an obstacle avoidance perspective, in planning, in the end module of planning and control. And we've done quite a bit of work in some of the mitigating the uncertainty that's propagated through some of these arrows, and I'm showing some examples of these uncertainties that we've tackled in our own research, as well as some of the references. But today, what I want to focus in on is this arrow between tracking and perception. So what do I mean by uncertainties between these two? So first things first, object tracking is basically this problem of associating detections in like neighboring frames. So, you might detect a car, like I'll take these, parked cars on the right here as an example. You might detect a parked car and draw like a bounding box around it, but you need to make sure that that parked car that you detect in frame 1 matches the same parked car in frame 5 or whatever. And so what I'm going to show in this video are some of the common errors that come up when you are trying to track a lot of these objects through time. So here we can see, there's going to be 3 types of things: false positives, ID switches, and something called fragmentations. So ID switching is basically where 2, objects are quite close to each other. And so they might get mistaken for one another at tracking time. And so you might say, oh, this parked car actually it's actually this other parked car, which is incorrect because, they were just very close and your algorithm got confused. Another type of error is a fragment, where basically, one bounding box might occlude another bounding box, and so it kind of cuts that track in 2 because something passed in front or something like that. And then a false positive is simply where you detect that there's something there, but there's nothing actually there in the real world. So these are kind of the very common errors you'll see in tracking, and what they kind of look like in a real autonomy stack. Now, the problem with having these tracking errors is that they really detrimentally affect modules that are downstream. So I showed you in that earlier example that an error in detection or tracking kind of propagates through the rest of the autonomy stack. So I'm going to show here how an example of how tracking errors really detrimentally affect prediction. So on the left here, we can see pretty reasonable predictions. So these are these like yellow lines that are like emanating from a vehicle that just finished doing a left turn. And we can see that these are like, without knowing much else about the map or anything, these are pretty reasonable predictions, right? The vehicle is probably going to continue straight. Maybe it goes to the left or right by a little bit. But the problem is, if we have like some false positive detection that then, your tracker mistakes as belonging to your actual vehicle, then it might look like your vehicle did some left turn and then very quickly, jumped to maybe turning right or something like that, which then causes your predictor to like, swing wildly to one side, which is, obviously really incorrect. And actually, when you look at this over like, a real world data set, prediction errors under these kinds of tracking errors increase by 10 to 30 times. It's really, there's like a sharp increase in cases like these and others. And so one of the core questions that we asked in our group is, how can we make prediction more robust to these kinds of errors? And the core question that we kind of asked was, is tracking, like actually solving this problem of, associating things between frames, actually necessary to make predictions? And really the key idea that we had and that we wanted to evaluate was, can we just directly use detections and their like similarities between frames as inputs to a prediction model, which, in this case, we used a transformer type of neural network. Can we directly use these two together and skip this kind of need to do like a hard data association? And data association is basically, like I said, where you're comparing, 2 bounding boxes in adjacent frames, and then saying, yes, this box is the same object as this other box. Can we kind of skip doing that step, which can be erroneous? And we saw that when we actually did, deploy this type of idea, prediction errors in these same cases where there was tracking errors decreased by like 40 to 80% when using this, I'll call this affinity-based prediction method, where you kind of use these similarities between time. And to show you what this looks like, so here on the left, you can just see a standard, pipeline that's doing like hard association tracking, and then one on the right, which is using our method. So you can see that when there's like, false positive detections, some of these parked vehicles look like they might suddenly move. Whereas in our method on the right, you can see that there's none of these like predictions that are emanating from those same vehicles, even if there's like false positives, because our method learns to kind of filter out those like single frame errors by looking at, more of a history of where objects are. So this is like, one way that you can handle, let's say, some of the uncertainties that come from perception into prediction. But now if we turn our focus downstream, there's also, after prediction typically comes planning and control. And I can tell you right now that kind of the predominant output representation of prediction is usually something called agent tracklets. This is just a fancy word. Really, all it means is that when people when methods make predictions, typically they're outputting just a set of points, like a set of temporally linked points, which is typically, future positions, velocities, accelerations, orientation, whatever. But the question really is this the best representation for planning and control? And especially, this is especially like a relevant question if you're doing something like optimization-based planning and control, which usually reasons about system dynamics rather than something like, this, which is like kind of regions to avoid. And so another project that we did, and this was some work I did during my PhD, was basically to investigate more efficient output representations from prediction that play more nicely with the kinds of structures that planning and control algorithms are used to. And in particular, what we did, the key idea here with this work was to reason about prediction representations as actually system dynamics that we're outputting from, these prediction neural networks. And the key idea here is that we're outputting, you can ignore everything else on this figure, but the key idea to keep in mind is that from prediction, we can output some kind of intermediate representation. And then that intermediate representation, you can still produce agent tracklets. So you can still, calculate how accurate your predictor is. You can calculate how, you can visualize where agents might go in the future. You can do everything you could before, but this intermediate representation, you can directly pass into planning and control. And that's a much more like intuitive representation to work with from a planning and control perspective. So what I'm visualizing here, this is something called a linear time varying system. So this is actually what this, the form of this equation is. So those of you taking, controls classes or who have worked with this might be something that you've seen before. But basically what we can do is, we can have our prediction methods output, some of these components of these system dynamics matrices and use this, we can output many of them over time and use this to actually represent how multiple agents in a scene might evolve in the future by simply unrolling their dynamics. And so you can directly use this in something like a model predictive control framework in order to, choose which action might be the best for, the autonomous vehicle that you're driving. Now, something else that we can do, rather than maybe this is too much of a shift, right? Maybe, changing our entire output format might be a little bit, difficult to reason about. It might be, difficult to actually make work in like a, where you need safety critical systems. So something else that we can do, and this is another project.
Of course. Quick question about the previous method.
Of course.
So over here, like you said, you could use this in a model predictive framework, model predictive control framework. But the predictions themselves are kind of linked to the actions that your robot takes, like at time t, let's say you take an action versus if you've taken some other action that would have led to a different set of predictions for the future. How would you take that into account while kind of feeding this to an MPC-like framework?
Yeah, explicitly. So actually, it's a great question. So this framework is explicitly designed to work with the idea, like we designed this with optimization-based controllers in mind, where your decision variable is going to be something like the controls of the autonomous vehicle. And so our term here, this like control term, explicitly has this UR, which is the control of the robot. And so the idea is, if you were to unroll this, it's explicitly taking into account the ego vehicle's like motion plan in the future. Yeah.
Understood. Thank you. Christoph has a question as well.
Yep.
Oh, yeah, just a follow-up since we already here. Yes, you said this is a linear system, and I guess in a current operating point, it might be a good guess. But if we have, let's say, like an NPC with a horizon of a few seconds, then there is some decision points along the way. Like I don't see how a single linear system can, adequately model the system, right?
Yep.
Because there's mode switching, right?
Yeah, it's a great question. So there's kind of two ways that we handle this. The first is that it's not directly a linear system, it's a linear time varying system. And actually, I'm also even lying a little bit. It's not linear, it's affine, because you have this extra C term here. But what I can say, so that's the one thing. When you have an affine time varying system, it's kind of, you can almost think of it like, I don't want to say piecewise linear, but you can almost visualize it, right? Like if you have a lot of linear functions, you can, because we're going to constantly, as you said, we're going to constantly linearize about some point, and we're basically going to be linearizing typically about whatever we think the like ego vehicles, like, because we have the motion plan for the ego vehicle, so we can kind of do that as it unrolls forward. But the other thing also that I kind of hid when I was talking, this subscript Z stands for kind of prediction modes. So we don't just predict one unrolling of the future. We'll predict multiple unrollings. And so that's where
sounds good. Thanks.
Yeah, no problem. No problem.
And we have another question from Jeremy.
Hi, Boris. Can you hear me?
Yep, I can hear you fine.
Oh, thank you for your presentation. And yes, I have a quick question of this new presentation of the prediction. This presentation is only suitable for the known type of the objects, for example, the pedestrian or the car, or it's also suitable for the unknown agents, for example, from the clustering, something like that.
Yeah, this is a good question. So you're right. We assume that we know the dynamics models of the like different agents that are in the scene. Oh, and you're right. If we don't know, if it's like an unknown type of agent, the best we can do is basically assume some very general dynamics model. For example, we might assume a single integrator or a double integrator, like as if it was some kind of particle. Okay. So we basically, you're right. When it comes to unknown types of agents, we would have to make assumptions, which hopefully are borne out in the real world. But otherwise, yeah, we can't really do much better if we don't know much about that specific agent.
Okay, that's a very good idea. Yeah. Okay, thank you.
No problem. Thank you guys for the questions. So yeah, continuing on, what I wanted to continue was saying that something else, some other types of directions that you can take when it comes, in this direction, in this interface between prediction and planning, is you can also just take a look at what's important, other factors that are important in planning. So one is something called scene consistency, which is basically, if you're making predictions for agents independently of each other, like let's say you have some type of trajectory forecasting model that just looks at one agent and maybe its surroundings and makes a prediction for it. This is nice because you can do a lot of things in parallel. But the problem is you might have joint, like when you now start to merge predictions together, you might have these like predicted collisions, which are like maybe in like a marginal probability sense, they're likely, like each agent here could go forward, but the joint probability of both of them going forward at the same time is very low. And so the problem is when you have a lot of these like independent prediction models, you might get these kinds of wonky joint probabilistic scenarios that really are not borne out in the real world. And so, something that we can do in order to mitigate this. So talking about that same idea of having multiple prediction modes, something that really helps with multiple prediction modes is that you can kind of disambiguate, some of the different, like the different modes of interactions between multiple agents. And this you can do when you kind of realize, when you reason about the entire scene together all at once, and you can take into account interactions. So one of our other latest works, this was from this year, was basically grouping agents into cliques, what kind of agents that are nearby, moving in the same direction, maybe have similar type, grouping them into cliques and reasoning about their joint futures in order to basically, make sure that you have self-consistent predictions, at least within those cliques. And so some features of a work like this is that, you're going to want these things to be temporally dependent because, agents move and they might move alongside one another, or they might kind of move out of the scene. And so you can see that, if I'm coloring things here by like cliques, you can see that, as this agent moves up or some agents come closer together, they'll change cliques. But also something that you can do is when you reason about agents' interactions, you can also do some interesting probabilistic things like condition on, things that you might want to happen. So here I'm just showing these are just normal predictions from the model. Car is just moving forward, really nothing fancy is happening. However, if we basically ask the model, what happens if the blue and this green agent, these vehicles slow down in their lanes, we can see that the model actually tells us like, oh, okay, maybe this brown and purple agent behind them will have to slow down or like change lanes to basically avoid them. So you can also have these very interesting like what if questions that you can ask your model when you do reason about interactions in like a structured way. And then finally, the other question that you can ask is, I've kind of made an assumption going through all this, what I've been talking about, saying that, there is like kind of this one architecture, which is you have perception, you have prediction, you have planning, and they go one after the other. Now, that is something that's quite popular in, with a lot of the AV companies in the space, including NVIDIA. However, of course, there's been other lines of work which basically show, can you, just go directly from sensing to driving commands? And this is kind of like an end-to-end architecture. And this has been espoused by, also another few companies. And the question here, and usually it's kind of seen as this big divide between, one type of architecture and the other. And one project that we had in the group recently was basically, can we maybe view these general types of architectures as a spectrum? Basically, is there a way to maybe combine the best elements of both, where, in modularity, you have interpretability, you have these nice intermediate outputs that you can visualize, and you can it can help debug, when things go wrong. But the problem is at integration time, it's very annoying because, you might have a problem in prediction that then affects, 3 different things down the road. In end-to-end AV architectures, they usually perform very well, but you have no idea what's going on inside. And it's very difficult to make changes to specific components if you want to try and, incorporate some prior information that you might have about the environment. And so another project that we had in the group was basically combining the best of both by creating a differentiable modular stack. And so the idea here is that you can have, these interpretable and reusable components, these different modules, but by making them all differentiable, you can then fine tune them end to end to basically have their interfaces tuned to basically work the best together. And what we saw was that, when you have just a standard non-differentiable, very standard autonomy stack, you can get, good performance, you can get, let's say 71% of the cost relative to like some theoretical maximum performance. You can get good prediction errors of, averaging 1.3 meters. However, when you then combine everything together and have this differentiable fine tuning, we can see that our prediction performance drops even a little bit. But even better is that our overall planning cost improves pretty, I won't say drastically, but pretty significantly. And so this is another idea of kind of how you might be able to combine, or at least, make these interfaces between modules better, so that they can actually work together to, improve overall system performance. So before I move on to the next part of the talk, are there any questions about these first few research works that I showed? Go for it.
All right. Yeah, I guess the question I have is, yeah, I would appreciate if you could expand a bit more on one of the first works you were talking about, doing this trackless prediction. Yeah, I would appreciate if you could just go over that again. I'm not really sure. It was a great example where, let's say, a perhaps erroneous track because of well, this could be because of velocity misprediction. This could be because of localization errors that would make, let's say, a parked vehicle look like moving, and then obviously, yeah, your prediction will react to that. how is that if you skip tracking, prediction is going to avoid this problem? Is it because it I don't know, tries to kind of regularize what you see? Like, yeah, like, I don't think I fully understand the example.
Yeah, of course, no problem. So it's a good question, because you might think, can't I just Kalman filter or something like that to basically do myself the smoothing, or like as an example of like something else you might want to try. The nice thing about this, so in particular, there's a pretty big reason why we used transformers as like the neural network architecture of choice here, and that's because, so transformers, they have this very nice self-attention structure, which basically allows them to look at any. So let's give an example here. If we're predicting, I don't know, we're predicting the next X seconds, and we're taking as input, let's say 3 frames. And let's say that, there's this like yellow, I don't know, erroneous false positive here that's then not found on either end. So what this transformer can do within its kind of self-attention structure is it can basically, if this specific object is kind of not replicated anywhere, since you're predicting from the current frame, it can look at these, this blue, red, and blue, green, and red objects and assign a very low attention to whatever this yellow detection was. So it's kind of like you're allowing the network to choose how it filters. It's like kind of to choose how it takes into account this historical information. And in reality, you're letting the network do its own type of like soft tracking internally. And so in particular, again, I purposely hit a lot of details here just to keep the like core idea, but it's kind of good that you're interested in this. And basically the core thing here, because it all relies on the self-attention structure. The core thing here is that we take these affinity matrices and we multiply the entire attention structure with them. So it's kind of, if 2 bounding boxes are very similar, then we'll keep whatever attention that the network gave it, we'll keep that at that same value. But if the boxes are very far, or they're oriented completely differently or something like that, then they'll receive a very low weight just from the just from how similar they are. And this like the function that generates this doesn't have to be fancy at all. It can just be distance based. It can just be distance of.
That's all fine. I mean, I was just really, I guess, really thinking about the example that you gave at a higher level, right? In terms of sort of what would in the end make the predictor ignore the potential uncertainty from, let's say, localization or state estimation of the vehicle. And I can see that if we're talking about predicting interaction between 2 agents, then seeing what the other agent is doing can sort of help disambiguate and essentially say, well, no, this vehicle is not moving because the other vehicle is not reacting to it. But that has caveats. Number one, it could be that the other vehicle doesn't see the other vehicle moving. That's number one. So there is a risk there. And then the other thing is, if the vehicle that was supposed to react is ego, then also this would not help, right? Because you would be observing, the actual action of the other vehicle, and you would have to respond to that. But yeah, I guess it's we can take this offline.
Yeah, I mean, I think the very quick answer is basically the network is really, like it has visibility over all the detected agents at the same time, and it's taking all of those as input. So it's like you said, it can see, or it can like reason about the interactions that it's seen over the past and use those to inform its kind of predictions for the future. But also, like a lot of the errors, these like tracking errors, they're not even related that much to like, like specifically like, 2 agents like driving next to each other, and then, one does something here. We're talking like even simpler stuff like false positives, which cause like a sharp change. Like already like handling that internally saves you a lot of these errors. And then these like interesting cases, they're like much rarer
Yeah, just basically adding, like let's say behavior model, because you were trying to predict, and you're adding a behavior model that just helps to reduce the uncertainty. I mean, I guess that'd be the short answer there. Yeah, thanks.
Exactly, and using data to basically inform that. Yeah. Yeah, Benjamin.
Hi, I had a question with regards to the joint prediction.
Yes.
So my understanding with joint prediction is that the joint space grows exponentially in the number of agents you have to predict. I'm curious if this is a problem you encountered, and if so, how you resolved it.
Yeah, excellent question. This is the entire reason we chose cliques. Because at least, you're right, if you look at the entire scene and you have yourself, you're trying to reason about, because, if you look in the paper, we really try and like correctly probabilistically reason about like all of the agents' interactions, and you're right, grows exponentially. You can't even hope to do it. With cliques, when you focus on a smaller subset, it's still exponential, don't get me wrong, but it's a much smaller. Like you're basically mitigating it by simply, having this kind of locally focusing your computation energy versus focusing on the entire, like interactions of the entire scene where most of them don't matter, or like most of them are very far apart. But yeah, no, it's, we're not breaking like fundamental limits here. We're simply better allocating where those kind of fundamental annoyances come up.
I see. Thank you.
Thanks for the question. Okay. Excellent. So with no other questions, I will continue on to evaluation. So in evaluation, the core question generally becomes, how can we measure an autonomy stack module's performance? So like I said before, suppose that we have this like perception, prediction, planning, whatever. As of right now, there are lots of metrics that you can find in the literature that show the performance, that can evaluate the performance of object detectors, of object trackers, of object classifiers. There's also a lot of metrics for evaluating the accuracy of predictions or the diversity of predictions, whatever. The problem becomes, how can you reason about these metrics when you're actually now integrating everything together? Because an excellent perception, stack, even if it's like 95% correct, is that 5%, is that causing some big problems in prediction? Or, how good is prediction actually for the thing that you need it for, which is planning and control? And to dive a little bit deeper into this, a lot of the metrics that I mentioned before that are used to evaluate prediction and detection are predominantly accuracy based, which means they'll usually compare kind of the ground truth, like from data, with what your model is outputting. So in prediction, I mean, I have a mosaic here, but kind of prediction has a lot of these types of metrics. Detection has also quite a few, but they're generally centered around something called intersection over union, which kind of looks like this. And this is kind of, you can evaluate how well your detected bounding box relates to like an annotated bounding box that you get from data. Now, where this becomes tricky is that these metrics, while they're really good for like getting a sense of the performance of these modules in isolation, they're task agnostic. And let me illustrate what I mean by that. So in prediction, let's say that the blue is the ground truth. That's like what actually happens in the future. And I make these two predictions, one in purple, one in green. Theoretically, these are equally inaccurate, right? They're only, they're both on this, the circumference of the circle. So they're kind of this many meters away from the ground truth. The problem is in one, if you mispredict that this car will come very close to you as the ego vehicle might have to enact some type of like safety maneuver to avoid it. Whereas if you make the other mistake, it's completely harmless because it's like, oh, okay, it's actually going to be even farther away from us. And the same kind of idea you can see in detection, where you might have some detector that maybe misdetects forward or behind, and one of them means nothing from the perspective of the ego vehicle, but the other one you actually might have to kind of move a little bit to the left to avoid it. And so, one of the goals of evaluation, and specifically this project that I'm describing, is how can we bring an element of task awareness into these otherwise task agnostic evaluation metrics. And the core desiderata that we came up with was, one, of course, we want to be able to capture these asymmetries in downstream tasks. But two, while we want them to be task aware, you want to stay method agnostic. So in particular, you might want to have a metric that is, aware of maybe the planning, like the planning cost function or whatever that you might use, but you really don't want it to be like, it only works if you use FMT star as your planner or A star as your planner or whatever. You don't want it to be tied to some method, because then that's not really generalizable to like, a wide range of approaches. Of course, you want these things to be, computationally feasible to compute, because ideally you want to evaluate these metrics over huge data sets. And then I'm going to use this term loosely, but you would also want these metrics to be interpretable in the sense that if you get some bad value for a specific example, you want to be able to realize, recognize, oh, it's because my prediction was, let's say, too close to this vehicle or not. I basically here, I just want to say, I don't want to use a deep neural network to classify if something is good or bad, because then I have no idea how it's getting to that result. So the core idea that we had with this line of thinking was, okay, if we want, the task that we have in mind here for autonomous vehicles is generally going to be something like planning and control. That's kind of the last module that, directs the vehicle where to go. And so one idea that we have here is, okay, can we learn a proxy planning cost function that accurately reproduces recorded vehicle motion? The core idea here is that, there's a lot of planning algorithms, like I said, FMT star, you can have optimization-based stuff, whatever. But we don't want to tie ourselves to a method. So if we step one kind of degree of abstraction higher, we can get to planning costs, which is generally what all of these methods are trying to minimize. So it's kind of a planning cost acts as like a nice general structure that at least informs what you want your plan to do. And so the core question is, can we learn from data some planning cost function that accurately reproduces this recorded vehicle motion, and then take the gradient with respect to like different terms in that learned cost function, like, terms for perception or terms for prediction, to yield a measure of planning sensitivity. And I'll describe what I mean by planning sensitivity, but this is the core idea, is like, can we learn how important is perception and how important is prediction to certain, cases in planning? And I'll show here what I mean. But, in order to test this out, basically what we did was, we took some human motion data from, like a large scale autonomous vehicle data set. And then we took a set of cost function terms like distance to the nearest lane, heading deviation from that lane, jerk, et cetera. Very standard common like cost function terms that you might see in like a planning or optimization based control cost function. Then with inverse optimal control, we learn basically weights that, best combine these different terms linearly to come up, to create a cost function that at least, hopefully well reproduces this human motion data. And then the idea is to take the gradient of this cost function with respect to, let's say, the predictions or the detections, and see how, how sensitive is your planning cost function to those terms. So this is like a lot of, abstract thinking, but let me like show some core key examples. So again, keeping into this mind that planning sensitivity is like, how sensitive is the ego vehicle's plan to changes in the detections and forecasted trajectories of other agents? So the core idea here is like, let's take a look at detection first. So we want to basically identify when do detections like matter from a planning perspective. And so we can see here that like, so I'm coloring things basically, the ground truth is in blue, and the detections range in color from red to yellow, where red means that they're like not, their gradient is like very close to zero. It's kind of doesn't affect the planning cost that much. And yellow is like, it affects it, quite a bit. And so we can see here that like, if you have a false positive detection that's like right near the ego vehicle, or like a, like a false positive vehicle here, or like some false positive bicycle here, that's like really, that has a high effect on the resulting plan that your, vehicle will enact. And actually the same can be said of these like parked vehicles here. When you're only focusing on detection at like a single frame by frame, if these things start to move forward, they're very much going to affect your plan in that you will have to probably turn left or slow down or something like that. So it's a bit dumb in the sense of it doesn't know, there's no temporal stuff here because it's purely like a frame by frame detection. But you can kind of identify that these agents are important to detect correctly because they could affect our plan. And then in prediction, we can also, take a look at like which agents' futures really impact the ego vehicle's planning. And I'm showing some examples here of like, there are some here like are some pedestrians that are like crossing the road, and obviously they're going to affect the ego vehicle's future. There's here some merging vehicles that are going to affect, that we have to like keep in mind as they're going to be contending with us. And same, there's like a lot more examples here, but basically the core idea is that we want to reason about which agents, either their detections or their predictions, will have a high like resultant effect on planning. And everything I've described here, by the way, this is not something you would use online necessarily. The way we had this in mind was that you would bring this into your evaluation time. So it's kind of, you can use this as a metric. And I'm going to show here 2 examples of how you can bring this information into some metrics, these popular metrics that I was describing earlier. So there's 2 ways that we experimented with. The first is internally, where basically you can try and change internal metric thresholds based on planning sensitivity. The one example I'll give is, so this is like a precision recall curve, which is a very common way of calculating the accuracy of a object detection framework. And at the core of this metric is the use of that intersection over union in order to detect what is a like correct detection and what is a not a correct, like a missed detection, because the bounding boxes are too far or something. And so what I'm doing internally here is literally changing the threshold by which we say something is a true positive detection. Basically, for agents with higher planning sensitivity, you have to be more correct to count as a true positive detection. And you can see, so on the left here, I have just the normal precision recall curves for the object detector that was like used in, for like a specific object detector that was used in the new scenes data set. And on the right, I have the same PR curve with this like modified internal bounding box threshold. And you can see how now, of course, all the results will get a little bit worse because here you can kind of only perform worse because it's a much more stringent evaluation idea. Another thing that you can do is, okay, even if you don't change the metrics, you might be able to striate the metric values based on the ego vehicle's planning sensitivity. So here I'm taking a look at some like common prediction metrics, like average displacement error or the log likelihood. And I'm basically grouping them into, to see how does, my favorite prediction algorithm perform on, let's say, vehicles. But in particular, what's nice to see, for example, in this plot is that, for vehicles that have high planning sensitivity, i.e. they will like affect, they could affect the ego vehicle's plan strongly in the future, we can see that the error is the lowest. So that's kind of a little bit comforting, right, for someone, because you kind of want all of the errors to be made in your predictor to be in like kind of for where it doesn't matter, like where your agents are, they will probably not affect your planning sensitivity. And the same thing you can see for like pedestrian predictions here. Yeah, Christoph, you have a question?
I guess just a remark. So first, or 2 remarks. First, yeah, I really like this approach. It's cool as an analytical tool to really see what matters, and to identify the interesting uncertainties that can occur. My second remark is that one thing that I'm concerned that I don't think you could just rely on this type of metrics for the sort of counterfactual reason, meaning that. It might be that you make for example, significant localization mistake about a vehicle to which you're not sensitive. But if that vehicle was closer to you for the same reason why you made a mistake, you could have done the mistake also in a location where you would be sensitive, right? And so there's this the question, like when you, let's say, doing testing and evaluation, you kind of have to go beyond what you observe now to think about, well, what if kind of questions, right? So I think that That's just a remark. I wonder what you think.
Yeah, I mean, absolutely. Like, I think with stuff like this, it's like, when we're proposing a tool and showing like some ways of like thinking about how to use that tool, it's kind of it's basically what you're saying is, if I'm correct, is kind of we're getting more task aware, but not all the way there. It's just missing that extra step of like because it's almost maybe the like intuitive way to think about it is like it's almost like we're taking it's because we're taking the magnitude of the gradient and dropping the sign, right? It could be that it's something that will cause the planning cost to skyrocket or drop a lot, and maybe we don't care so much about those cases that drop a lot as an intuitive example. I think, yeah, I agree. I mean, I think the good thing is by proposing something like this out there, practitioners, maybe it is advantageous to drop that magnitude, and maybe the sign here is like another nice tool that can be used for classifying which errors matter or which don't matter. I think it's more just like we just want to get this idea out there and to really make sure that people are aware that like the metrics that everyone's using is kind of, it's not even like beginning to kind of address this problem. But yeah, I think you're totally right.
Thanks.
Thank you. Does anyone else have any questions? Because I mean, it's a good time actually, just simply because it's the next one as well. Yeah, Bing.
Hi, can you hear me?
Yep.
I just have a question about do you see a world where these metrics can again, be used in training the ones behind the point and not just as accuracy? Or
yeah, this is an excellent,
maybe as part of like focal loss, you could use selective backprop and just focus on the parts that actually are very sensitive and like focus not on the parts that are not sensitive, or
yeah, absolutely,
the direction of the research team.
Absolutely. So absolutely. Yeah, it's a great question. We absolutely I can give you one direct example of like something that we thought of, and you can almost think of it like one way that you could use something like this is in something like a boosting style approach. I hope I'm like using the correct term here, but basically where you weigh the errors that you make on, let's say, like planning sensitive agents or objects more highly than others. And so that could be very much like that's like one immediate way that you could use something like this in your training loop, where you don't even have to backpropagate necessarily through this thing itself, but you can just already use this to like upweight different examples based on how planning sensitive they are. But yeah, it's a good question.
Right. So like use it as regularization for the loss, basically, is what you're saying.
Yeah, either regularization or I mean, whichever term you want to say, but exactly.
Okay, yep. Cool. All right, thank you.
Thank you. Wise Lab.
Hi, can you hear us?
Yeah.
Yeah, I wanted to ask a question about, could you reiterate about how you classify each vehicle as a high, moderate, or low sensitivity?
Yeah, nothing fancy at all. I just did like a pandas cut, like a quantile cut, to basically just separate, groups of values by like, that they roughly have the same number of examples per bin. But nothing fancier than that, though.
No, I mean, again, the numbers at the bottom, the ego vehicle planning sensitivity value that you've given each one.
Yeah. Like I said, I didn't do anything special here other than I like grouped them based on their let's say the like numbers that are within each of these values. So it's kind of like in this bin, if there's like, I don't know, 200 or something examples, then it's kind of like I think when I did this, I didn't do anything fancy other than just to show like, hopefully keep these bins somewhat similarly sized, like the same number of examples per, and then just show like the kind of what you might be able to glean when you look at these bins. It's not like I myself manually looked at each of the examples and then classified them. I thought that would be a bit too much of a stretch. I just want to say what's a very simple thing that you could do as a practitioner. Simplest thing ever is simply to just basically almost like clustering, right? You just look at your the planning sensitivity values you get over a data set and just cluster them into let's say, these three groupings.
So you mean for planning sensitivity, it's how much each particular vehicle changed your plan. So to calculate that, did you remove the vehicle to see if the plan would change?
No. So this is simply the magnitude of the gradient.
Oh, okay.
Yeah, it's directly that value. Yeah.
Okay. Thank you very much.
Yeah, thank you for the question. I see someone else also has their hand raised with a Neil. Yep.
Yes, hi. Actually, I had a question regarding some slide that was presented earlier, if you don't mind. It was regarding that linear time varying part where you had like the state space and you had the A matrix and some of the components were. Yeah. So yeah, exactly this one. So you mentioned that the Z value on the left side actually is for different modes. So I like this idea because it directly feeds into the planner. But like, what different types of modes would you actually consider for? Would it be like a continuous space or the discrete space?
Yeah, this is a great question. Great question. In our work, in particular, we use a discrete latent space. And the way that we did that, we had like a discrete conditional variational autoencoder inside the model, and then you can use that to like output your discrete modes. Now, kind of semantically, what this allows, it's very tough for me to say, for example, yes, mode 1 is, all vehicles going straight, or mode 2 is all vehicles, you know what I mean? Like it's hard to ascribe, especially when it's over a scene. It's hard for me to give you like, a nice answer as to what each of the modes mean, but it basically just allows the model to kind of cluster out different types of interactions itself without kind of trying to average everything together and blur it all together and then result in like a poor prediction.
That makes sense. Thank you.
Thank you. Yeah, go for it. Crystal.
Sorry, I was just trying to unmute.
No problem.
Anyway, it was disappearing. Yeah, I guess this is just just sort of a thought, from the discussion on the sensitivity. I think it would be interesting, like in sort of the spirit of some of the earlier points you were making about sort of using downstream insights to resolve uncertainty or to control what's happening in earlier stages of the pipeline. So let's say like humans do this a lot. Like when you look at the neural connections within the brain, interestingly, the amount of neurons that go from the LGN, which is like the point in the brain where the vision nerves come in and start process, like the very initial processing before you go to the cortex. There's relatively few connections from that input into the brain compared to all the connections that actually go from the brain into that place to actually let's say prime and configure the filters based on context and attention and things like that. So I was thinking that this idea of the sensitivity to planning could be actually an interesting proxy for potentially directing, let's say, processing power in perception. Like, for example, we know that using, let's say, like multi-stage detection can give you very good results, but it's very costly. But you don't have to, let's say, generate, do like a, let's say, two-stage detection everywhere, but you could be doing in places where it matters, right? For example, you could direct it by this. Just a thought. Yeah.
No, it's. I wouldn't even counterfeit it by saying just a thought. I think that's one of the core motivations we had with this work was really not just at evaluation time, right? But like the idea that, at evaluation time, but like the idea that you can identify exactly what matters is really it's a great help for designing the system thereafter, and make what decisions you can make, as you said, kind of what decisions you can make at the detector point is, if we see that it's like, the specific agent, or we can even use this planning sensitivity, whatever, online or whatever, that would be such a great addition. So yeah, it's exactly I think it's one of the kind of core motivations for work like this. Yeah.
I think let's hold off on questions till the end of the talk then.
Yeah, I don't actually have much more. So yeah, that sounds perfectly good to me. And you guys will probably anyways have more questions about the next stuff. So so the what I want to conclude with here is a view a little bit towards the most recent work and the future. So, everything I've talked about in the past, this is, research work that we've had over the past, let's say 1 to 2 years. And then, some of the things that we've been working on much more recently. So one project I can tell you that I was just doing over the summer was taking, so we've developed all these great models, and in particular for me, we developed these prediction models, but they are typically only trained in Boston driving data, Singapore driving data, Palo Alto driving data, right? Like, you only are training these models on like heaps of data collected in like a few geographic regions of the world, right? And so the question is, how can we actually develop systems that then generalize to things that you might not see in your data, right? Like, there might be different customs or laws or like vehicle types, as someone asked earlier. And so the question is, what can we do about this? And so one idea that we evaluated was combining meta learning with prediction. And meta learning is like this recent paradigm that basically studies how models can adapt their weights to data observed online. And so I'm showing an example here on the right of kind of, without observing anything, you might have some like prior, prediction of how things evolve. But then as you're observing more data, this prior, prior times likelihood, your likelihood is getting updated by data, and then your posterior actually becomes much more and more accurate and much more tight to the specific case that you're observing. And so the core question we have is basically, can we combine this idea with trajectory forecasting models? And I mean, the answer is hopefully yes. So, we evaluated kind of two settings. One is, adaptation online, where it's kind of you train your method in, I don't know, some data collected from, I don't know, let's say Palo Alto and Boston, and then you try and take that exact, those weights and apply it to data from Singapore, which, for example, they drive on the left-hand side of the road. And so, I'm showing here like a video of what that adaptation might look like. I mean, this is an example I took from our model from the paper, but basically the core example is, how online you can very efficiently make updates to your model that are very, they're not computationally intensive at all. This is something you can do kind of, very quickly in real time. But something else you can do is, okay, you might say, okay, I don't want to, that feels very scary, right? To have my predictor update online as I'm driving among other agents, that's too much. So what you can do is instead you can collect a little bit of data and annotate it offline. So, you have someone drive around and collect the data in the target city, and then you can annotate a little bit of it. And then what we show here is basically that our method, which is kind of in these like two blue colors, just from a couple hundred data points, can already very rapidly adapt and have its like, here I'm showing expected calibration error, but there's other, like in the paper, we have a lot more metrics for like accuracy and performance. And you can basically see how just from a few updates, it really drops, the like errors and accuracy improves quite a bit very quickly. Something else that we were looking at is, this is another really key direction. I'm not going to say too much about this, but this is another very big direction in autonomous driving in general, is simulation. Closed loop simulation is going to be really important as we try and scale out verification and validation, especially with, the desire not to test everything in autonomous vehicles on the road in real time. And, the core idea here is that we're using data-driven human modeling, or really prediction models, to, actually provide the actions for each of these agents so that they're, hopefully human-like and actually reasonable to work with. And the nice thing about this is you can actually, we were mentioning some counterfactual, like there was comments about counterfactuals before, but here, what's nice is when you use these kinds of models, you can generate multiple diverse rollouts for the exact same scene. Okay, so switching now to future directions. So, I talked a lot today about uncertainty and uncertainty propagation, but many prediction models still don't really focus on producing because they'll produce like distributions or samples or trajectories or whatever, but these outputs are very rarely calibrated. And so, while I discussed a lot of works that address number one, this is still quite an open area of research. And then, yeah, I think another big thing. So, a lot of my discussion today was about kind of the interfaces between modules. And I think there's still a lot of open questions. Obviously I focused a lot on this, kind of cascading structure, but there's many other types of structures, right? You could have perception directly feeding into planning control, which internally uses prediction to evaluate motion plans. And that's a very reasonable thing that you can do. And it probably, it might even perform, might perform better or probably does perform better. So I think there's a lot of questions along these lines. And I think the best part is, and why I'm very happy to speak to, students here today, I think right now really is a great time for autonomous vehicle research. Obviously I'm going to say this, but there's been a significant growth in the data that's available publicly since about 2019. Unfortunately, each of these data sets have a unique format, so this can be quite annoying to work with as a researcher. But the final thing that I want to present is that this is actually something that we've been working to remedy in our group. So we've developed a unified trajectory data loader, which provides a single interface into multiple sets of data. It's available online. It has an Apache 2 license, so it's all open source. So take a look there if this is something that this is some of the research that you're going to be looking into doing yourself. And then to really finally conclude, I think the key takeaways of what I wanted to get across today was that prediction itself doesn't operate in isolation. Its inputs are perceived and its outputs influence downstream modules. So revisiting these interfaces, I think, is a really important area of research. And I think it's actually more effectual than simply improving the modules themselves. And then, evaluation metrics are probably lagging behind a lot of these, a lot of effort in, improving modules. And it's important to develop metrics that actually really capture what we care about in autonomous vehicles or even in robotics or other spaces. And then lastly, I also want to really impress upon you that even though you might, there are autonomous vehicles driving around today with customers and whatever, there are still many, many open problems that necessitate further research. So with that, I just want to say, if any of this sounds interesting to you, I'm very happy to answer questions, of course. But I also really want to point out that we have our summer 2023 internships. There's a link here. And I think I highly encourage, if this is something that you're interested in, to apply and maybe we'll work together in the future. So with that, I want to thank you all. Everything I discussed today, absolutely everything I discussed, is open on archive. You can read any of these papers. I have some of the links here. And with that, I'm more than happy to take any questions.
Thank you so much, Boris. That was a great talk. And guess Wise Lab had a question, so we can start with that, and then we can open it up for others.
Yep.
Yeah, okay. There was this slide a while back that talked about the planning and how there was something differential about it, but I'm not sure I understood it properly. Could you go over that again?
Are you talking about this specific? Exactly. So the whole idea here was basically, as I mentioned just a little bit earlier, is basically a lot of stacks today, they have these modular structures, which is great because, you can interpret them, blah, blah, blah. However, cascading errors can be quite annoying to deal with. But then on the other hand, you have these end-to-end AV architectures, which they kind of do everything in one large network, and you can kind of find, you can backpropagate through the entire network. And so the goal of this research is basically, can we keep this modular structure, but still have the ability to do end-to-end fine-tuning? And in order to do this, you basically have to come up with, you have to create, these modules have to be differentiable so that you can pass, gradients going backwards through it. And so, yeah, I think, I mean, this was kind of the core element of this. Are there specific questions that you had related to like this architecture, or?
So the whole thing is differentiable. I remember reading a paper on the Apollo driving system, and in between each of these modules, they had a whole bunch of code that would work to filter everything and correct incorrect tracks and outputs. So all that has to be made differentiable, or it has to be thrown out, right?
Let's say more or less, yes.
Okay.
Yeah. So this, I mean, we don't use the like Apollo stack here, but I think what you've said is basically, it's a very good point, right? There's a lot of these kinds of like non-differentiable operations that a lot of people do, but kind of behind the scenes between these modules. And I think, yeah, this is exactly something that like ideally you would want to avoid. And so this is kind of what we're trying to slowly but surely break down those instances of like tons of just non-differentiable stuff together.
Okay. Thank you very much.
Thank you. Christoph?
All right, yeah. So I guess, well, I have maybe some discussion points about your future direction slide, one on different ways of integrating prediction into the stack. Yeah, exactly this one. So yeah, so I guess yeah, we can think of different arrangements here, and clearly one can, yeah, if you're using sort of traditional MPC-like optimization methods, yeah, it could be more traditional predictor, but in the end with horizon and so on, you're gonna need prediction for the more interactive type of
yeah, one example I can immediately give you that kind of looks like this bottom one is policy planning, where you kind of evaluate, you can do like a graph search, and then at before expanding each one of those nodes, you can run your predictor as one example of this like architecture here.
Right. Yeah. But basically, so there's a range of possibilities. You can use sort of more classical. Then you need a predictor as a kind of explicit model of the world to do the rollout if you want, or you could well, but you could also have just a policy, right? And then I guess the predictor could be used there sort of to watch what's happening and whether the policy is reasonable, I suppose. But you could also take the predictor and sort of make it conditional and just use it as a planner right away, right? And I guess that sort of something has been proposed, and yeah, I kind of just wonder, on the latter, like, what is your thinking about that? How?
Yeah.
Well, is this an approach that you think would make sense in practice, right?
I mean, well, when the word practice is thrown around, then then all bets are off. Usually because
I mean, otherwise I wouldn't think, because in research everything is possible, right?
Yes. Yeah. No. So one thing I can say when it comes to different architectures, and we are actively exploring / even doing this kind of stuff at NVIDIA. So it's kind of like, as long as you are satisfying, general constraints and getting, and of a lot of them, but as long as
you can have a monitor for that, or a backup planner, just
like there's a lot of this kind of stuff you can do. And long story short, all I wanted to say was, I'm glad you said conditional prediction, because this is, it's absolutely something that you can simply use your predictor to basically give you an estimate of your cost to go, or like your estimate of your kind of future cost, and then have that rank stuff. And at the end of the day, if you think about it, there's nothing really super scary about using something like a prediction module to rank your like candidate motion plans. It's a very natural part of a lot of I think it's like a very natural part of a lot of motion planning stacks, is that they use like you'll use a ton of like heuristic ranking and checking and scoring, like trajectory scoring methods. So I think even if you just add prediction as like, one extra signal into the mix, I think it's already a big change without necessarily like, going overboard and like directly, let's say, outputting motion plans from a prediction module. But even if you wanted to do that, I think you could still do that because you can output directly motion plans from a prediction module and simply use that to, for example, initialize your search, or even use that as another candidate in your search. So you don't have to like throw any of the guarantees. You don't have to like throw any of the other structure you had away, but simply if you add this as an option and it's ranked as a better option, excellent. Then you can directly use that kind of human-like trajectory. So it definitely, so I don't even have to say that it's like, that practicality is scary or something. It's simply, you just have to find those ways to insert it into those existing structures. And then if it turns out it's just getting picked as like the correct, candidate all the time, then even better. You have all your safeguards, but simply, you know that your model is actually a very good, like, warm starting method, as an example.
Yep, thanks.
Thank you.
All right, if we don't have any other questions, guys, let's thank Boris again for the great talk and for the excellent discussion. And Boris, a question was asked. Could you share your slides with us, or?
I think I can. If it's okay with you, I'll probably share it as like a PDF.
Yeah,
I don't know if it matters. Okay.
Absolutely. Yeah.
Okay. And then, I highly encourage, if any of this is interesting, highly encourage you guys to take a look at our internships. And hopefully maybe we'll work in the future together. Thank you all again very much for your time.
Thank you so much, Boris. All right. Thank you, everyone. Thanks. Have a good one.
Yeah, thanks.
Should I send them directly to you?
Oh, yeah, that would be good. If you could just email them over to me and I'll forward them to everyone on the mailing list.
I can do that, no problem.
Awesome. Thank you, Boris. Thanks again. Have a good one.
Thank you. Bye-bye.
Thank you, Boris.
Bye.